The paper of the day is Combining Systems and Databases, a Search Engine Retrospective. Although a search engine manages a great deal of data in response to queries, it is not accurately described as a database or DBMS. We believe that it represents the first of many application-specific data systems built by systems community that must exploit the principles of databases without necessarily using the database implementations. This paper presents how a search engine should have been designed in hindsight. Although much of the material has not been presented before, the contribution is not the specific design, but rather in the combination of principles from the largely independent disciplines of systems and databases. First, authors present the design using the ideas and vocabulary of the database community as a model of how to design data-intensive applications. They then draw some conclusion about the application of database principles to other out-of-the-box data-intensive systems. Design principles. The problem with using existing DBMS systems to build a search engine is that they are not traditionally designed to handle full-text search. Search engines also do not need strict ACID semantics and usually prefer high availability over consistency. Furthermore, search engines are able to clearly separate out updating data from querying data, and each portion that can be optimized as needed. An observation made by the author is that although search engines largely involve complex data management, they generally do not use databases to do so. However, many of the design principles that guide database implementations can be leveraged for search engine development. The core hypothesis here is that, looking back, search engines should have used the principles of databases, but not the artifacts, and that other novel data-intensive systems should do the same. Here are some of the design principles. Top-down design. The traditional system methodology is bottom-up in order to deliver capabilities to unknown applications. However, DBMS are designed top-down, starting from the desired semantics, example ACID, and developing the mechanisms to implement such semantics. So, search engines are also whole designs in this way. The semantics are different, covered below, and the mechanism should follow from the semantics. Data independence. Data exists in sets without pointers. This allows evolution of representation and storage and simplifies recovery and fault tolerance. Declarative query language. The use of language to define queries that says what to return, not how to complete it. The absence of how is the freedom that enables powerful query optimizations. We do not, however, use SQL, a DBMS artifact, but we do use the structure of a DBMS. The query parser, a rewriter, a query optimizer, a query executor. They also define a logical query plan separate from the physical query plan. If designing a search engine from scratch, the focus should be on the supporting many concurrent read-only queries with a focus on availability more than consistency. This focus leads to an architecture where the database is largely static and updated using asynchronous workers that rebuild and update the database periodically. Crawling, index, and serve. Providing the basic operations of search engine involves three steps: crawling, indexing, and serving. First, web crawlers fetch documents from the web and output them as a list or maps of visited sites. Second, an indexer parses and interprets documents, outputting a chunk of data that serves as a portion of the static database. The indexer scores and ranks documents, minimizing the work of the query processor. Finally, the server executes queries against the chunk output by the indexer. Queries. Search engine queries differ from the SQL queries but can still undergo similar query plan optimization steps. A search engine query defines words and some properties that matching documents should or should not contain. Queries combining words and properties such as query language or Boolean conditions. In the simplest case, a query is a list of terms and matching documents that must contain. In more complex cases, Boolean expressions and properties affect query interpretation. Search engine queries can be represented as logical query plans that can be implemented by a separate optimizer. The author contends that the separation of the query parsing and planning for execution is a key result that can be leveraged from the database community. In search engine, a query plan is turned to a very specific use case and need not support the general query semantics of traditional SQL queries. In the search engine case, plans are presented as joins on matching document IDs with some filtering where needed. Updates. The search engine index must be updated to return fresh queries results to users. In a search engine, each node is independent and can be updated without concern for other nodes. The authors also introduce a constraint that the whole table is updated at a time rather than individual rows within a table. To perform a full update, the first step is to get a new content through crawling. The result of the crawl is used by an indexer to update a chunk of data that the indexer is responsible for. The chunk corresponds to a range of documents after a chunk has been updated by the indexer. An atomic update to the chunk can be performed on the master dataset. Cache can be invalidated where necessary. In some cases, documents can be updated or deleted in real time, not as part of the indexing atomic update. The approach taken by the author is to add a new row to the chunk that means item deleted and add that filter to each query. The same mechanism can be used to handle updates. Periodically, the whole table can be updated with this data using the same process as updating a chunk through indexing. Fault tolerance. The primary goal of the fault tolerance in search engines is high availability. The problem can be subdivided by first determining what portions of the system must be highly available. Query servers rely on snapshots of data. The process of creating snapshots using crawling and indexing does not need to be highly available. Therefore, the snapshots themselves are primary target for high availability. The mods to having the nodes running queries coordinate a master for each query and electing a new master when a query fails. Failures in follower nodes are detected by the master and then a follower is selected to execute the query. These failures are handled by using replication. To recover from the complete disaster, clients can try alternate masters in the alternate data centers to resolve a query. Crawling and indexing can be restarted at will since they are idempotent. Search engines can leverage much of the top-down design work of database systems to produce a cleaner separation between semantics and implementation. This allows for semantics and implementation to evolve independently and provides clear partitioning of the system responsibilities. The same strategy can be used when designing any data-intensive application.